In this video, we're going to be taking a look at a projectile fired 50 degrees from the horizontal that is going to land on an inclined plane. Now, in order to do this, we're going to have to do some projectile concepts along with some substitutions. So first of all, let's take a look at stuff in the x direction. We're only going to be using this formula right here because for constant velocity, we're going to only use v equals delta x over t. So with that being said, we know that the velocity is 15. So we know that 15 times the cosine of 50 degrees is going to give us that horizontal component, and that equals delta x over t. Now what we're going to do is we're going to solve for everything in terms of t, because later on we're going to need to do a substitution. So we're going to go ahead and swap these, and then our time is going to be delta x divided by 9.64. Okay, also in addition to that, we're going to have to do another substitution. If you take a look at a simple triangle like this, and we have a y component and an x component here, which is basically like a delta y and delta x, how much it moves vertically and horizontally. We have this angle right here that is 30 degrees. That is our incline. Now, the way that they're related is by the tangent of the angle, because tangent is opposite, which is your delta y, over adjacent, which is delta x, which means that the tangent of 30 degrees equals delta y over the delta x. So what we're going to do is we're going to multiply both sides by delta x, and then that would give us the delta x times the tangent of 30 degrees equals delta y. Okay, so now that we set up some steps to see what time is in terms of delta x, and then also the relationship between this delta x and delta y as far as just analyzing the triangle, we are set to start the main part of our calculation. Now, if we take a look at the vertical components, we're going to go ahead and analyze it with this formula over here. And we know that if we want the initial velocity, that's going to be taking that 15 meters per second and then multiplying it by the sine of the angle 50 degrees. And then that's going to give us about 11.49 meters per second. Okay. In addition, we always know that the acceleration due to gravity is negative 9.8. Okay, so I'm already going to put some of my substitutions in as I'm writing it out. So instead of delta y, I'm going to use this over here that I have in orange. So I'm going to put in delta x times the tangent of 30 degrees. Okay, and then that covers my delta y. And then we have VI, which we just said is 11.49 times T. And then T is delta X over 9.64. So I'm going to go ahead and take care of that substitution as well. Okay, and then plus 1/2 AT squared. 1/2 A is going to be negative 4.9 because that's 1/2 times the acceleration due to gravity. So I'll just write it as negative 4.9. And then we also have t squared, so we'll do the same substitution we did earlier from this box. And it's times squared, so all of this is going to be squared. So delta x squared over 9.64 squared. Okay, so now we are actually all set up to find an important unknown variable, which is delta x. So the way that's going to work out is you can simplify it a little bit. We can go ahead and say the tangent of 30 is about 0.577, and we'll make that the coefficient in front of that delta x. We can take the 11.49 and divide it by 9.64, and that'll give us about 1.192, and that'll be the coefficient in front of this delta x. And then the negative 9 or 4.9 divided by 9.64 squared is going to give us negative 0.0527. And then that will give us the coefficient in front of the delta x squared. So now what we can do is we can combine some like components over here. So we can subtract this from both sides, which is basically just subtracting this coefficient by this coefficient over here. And that would leave us with negative 0.615 delta x on this side. And then that would equal negative 0.0527 delta x squared on this side. So one of those delta x's is going to drop out, and then that leaves us with just dividing both sides by this coefficient. And then our delta x comes out to about 11.67 meters. Okay, now I realize that I did kind of a lot of rounding there, so if you want to be a little bit more accurate, you could leave things like such as tangent and theta and then leave fractions in there. I just chose to just finish dividing and multiplying things just to simplify the look of it, although it's not the most accurate answer, but it's pretty close though. So we have a delta x of 11.67, which is good because now we have one more step, and then we can go ahead and find the point where the projectile is going to land on the incline. So that delta x is basically the horizontal component, but we want like the hypotenuse component over here. So what we're going to do is we're going to set up the cosine of 30 degrees from our incline. Okay, the reason why we're going to set up cosine is because we have 30 degrees here. We know that the horizontal component is 11.67, and we want to know what the distance is up this incline over here. So that's the adjacent and hypotenuse side. So adjacent over the hypotenuse, and then you can go ahead and cross multiply those two, and then you can find your distance that it lands on the slope, which comes out to about 13.48 meters. So when you work this problem out, because you initially have a lot of unknowns, you're definitely going to have to do some substitutions. So I did that early on. I solved for things in terms of delta x with my red box and my orange box over here so that we can drop those into this right equation and then have everything in terms of delta x. Once you find one part of your triangle and you already have an angle, you can definitely use a little bit of trig to find other components of your triangle, which we did, and find the hypotenuse to find out where it lands on the incline itself, which is 13.48 meters. So I hope that was helpful to you. Thank you for watching and listening.